We'll start this lecture with something I think you will think is really cool. We're going to look at two groups which you will see immediately are identical to D4, but they have different elements and different operations. Let's first look at the rotations of the square, r squared, r cubed, etc., to be permutations of the vertices. Well, then r would be which permutation? Well, let's think of 1, 2, 3, 4 as the vertices, and the rotation of 90 degrees counterclockwise would send vertex 1 to 2, and it would send vertex 2 to 3, and 3 to 4, and 4 back to 1. So that is a permutation from S4. And we know what r squared, r cubed, and r to the fourth is the permutation that doesn't move anything. A reflection across the horizontal, here's the horizontal, let's just look at that and call it H. Reflection through the horizontal there is also a permutation of the vertices. Let's call it H. H is equal to, well, it sends vertex 1 to vertex 2 and 2 to 1. It just switches 1 with 2 and, of course, 3 with 4. So now we've written H as a permutation. And here's the group right here. Now I won't call it D4. It isn't D4. But look, it has, here's r squared. You know how to square these things out. This is r cubed, and r to the fourth is the identity. Here's H, 1, 2, 3, 4, H. This is HR. This HR is 2, 4. HR squared is this, and HR cubed is 1, 3. And I leave that for you to just multiply those things out and see. But can you see that this is algebraically identical to D4? That's the topic of what we're going to talk about in this lecture. We call these two groups isomorphic. And right now you don't see exactly why they are, but you see that you have two elements of order 4. You have 1, 2, 3, 4, 5 elements of order 2. It's exactly like D4. Another way that we could view the symmetries of the square is by thinking of linear transformations of the entire plane. Which linear transformations of the plane R2 send the vertices of the square to the vertices of the square? You may remember from linear algebra, and if you don't, that's okay. We're going to cover that later. The columns of the matrix for a linear transformation are determined by what they do to the basis vectors. So our standard basis vector is 0, 1, and 1, 0. So I've labeled the basis vectors there on the x and y axis. So let's determine what would a rotation, I'll just write R90, a rotation 90 degrees counterclockwise. Well, let's see what it does to the basis vectors. The basis vector 1, 0, notice I'm writing them as column vectors. That makes no difference. It will send the basis vector 1, 0 to, well, a 90-degree rotation is going to send it up to 0, 1. And it will take the basis vector 0, 1, and it will move it to, well, rotate 90 degrees. It's going to move it down to the point minus 1, 0. So I'll write minus 1, 0. So we know what this rotation does to the basis vector, and therefore I'll call capital R the matrix that we're looking for. Let's call it capital R, and it will have as its column vectors these. So it would be 0, 1, minus 1, 0. That is the matrix for the linear transformation that rotates the plane 90 degrees counterclockwise. Now let's find the linear transformation matrix, the matrix for the linear transformation that gives us the flip over the x-axis, over the horizontal. So first we have to see, let's call it H. So what is it going to do to the basis vectors? Well, if you flip over the horizontal, the vector 1, 0 stays right where it is. And the other basis vector 0, 1 will be flipped down onto 0, minus 1. So this gives us our matrix H. H will be the matrix using these column vectors, 1, 0, and 0, minus 1. So now we have two linear transformations that represent the rotation of 90 degrees of the plane and the one that reflects it across the x-axis. So here is the matrix R, the rotation, and here is the matrix for the linear transformation that reflects the plane through the x-axis. And here I have R squared, R cubed is using matrix multiplication. Sure enough, R to the fourth is the identity matrix. And here I have H, HR, HR squared, and HR cubed. You can do those calculations yourself. Here we have a subgroup of GL2R, or I believe this might be a subgroup of SL2R. The determinants are 1. And this group G is what we say isomorphic to D4. It's exactly the same thing, just different names and different operation. But I want you to see how these linear transformations act on the vertices of the square so that you will believe me. Let's take our matrix R. This is R, and we're going to see this is R, and we're going to see how it acts on this vertex 1, 1, 1, 1. And when we multiply that, let's see, we get negative 1, 1. Now, is that what happens if we rotate it 90 degrees counterclockwise? Yep, the point 1, 1 goes to the point minus 1, 1. Here is H. Let's see how H acts upon the point 1, 1. Again, this vertex. Well, if I multiply the matrix times the vector here, I get 1 and minus 1. Well, that is true. If you flip over the horizontal axis there, 1, 1 goes to 1, minus 1. One more example. Let's see what H does to the vector 1, minus 1. It better put it up here at 1, 1. Let's see. If we multiply, sure enough, it sends this point to that point by reflecting over the x-axis. The three groups D4, the subgroup of permutations from S4 on the previous slide, and this subgroup of SL2 are algebraically identical. Mappings called isomorphisms are going to be how we can tell if two groups are algebraically identical, if they are what we say isomorphic. An isomorphism phi from a group G with operation delta to a group G prime, operation star, is a one-to-one mapping from G onto G prime that preserves the group operation. What we mean by preserving the group operation is this. Phi of A delta B is equal to phi of A star phi of B. Let's draw a picture and see what we mean by that. Let's say this is group G and this is group G prime. And we have a mapping phi. Now, phi takes G to G prime, And let's put A and B in G, and they each have an image, phi of A, and B, we have phi of B. And what preserving the operation means is that if we multiply in G and get A, well, let's write A delta B. If we do the operation in G and then map over, we're going to get phi of A delta B, right? But that has to be the same as phi of A star phi of B. In other words, it doesn't matter if we perform delta first and then map, or if we map from A, map from B, and then perform the operation inside of G prime. So if we're given two groups and we can define a mapping from one to the other that preserves the operation, and we can show that that mapping is one-to-one and onto, then we know that the two groups are algebraically identical. In other words, they are isomorphic, and we denote that by this. In our first example, the mapping is given to us. It says, let phi map the real numbers, that has to be under addition, to the positive real numbers. We're not writing the operations down, but we know what they are. In the real numbers, you know that we're talking about the operation addition. We'd have to take 0 out to have it be a group under multiplication, and the positive reals would have the operation multiplication. So let's define the mapping by phi of x equals e to the x. There are 3 steps necessary to prove that phi is an isomorphism. We have the mapping. We have to prove it's one-to-one, onto, and that it is operation preserving. So to prove a mapping is one-to-one, we start by, suppose, phi of x is equal to phi of y. Well, that would mean that e to the x is equal to e to the y, and we know that the function y equals e to the x is a one-to-one increasing function, and therefore we can conclude that x is equal to y. So the function is one-to-one. Phi is one-to-one. Now let's prove that phi is onto. So, well, to prove it's onto, remember here's r, and here's r plus. We want to pick a positive real number, y, and find something over here that maps to it. We got to find that. Pick any y in r plus. So let y be in the positive real numbers. Well, we know what maps. We know what maps to y. Let's just let, you wouldn't even have to say, name it x. Let x then be the natural log of y. Then phi of x is equal to e to the x is equal to e to the natural log y is equal to y. Therefore, phi is onto. Now you could, in something like this, you don't have to introduce x. You could just actually say this. Give yourself a y, e to the ln y is y, and you know the natural log of y is in the real numbers, so you've shown it's onto. Now we need to prove that it is operation preserving. So we start with phi of, now the first group is addition, so phi of x plus y. And let's just work it out and see if we can get to phi of x, phi of y. Well, this is e to the x plus y. And we know that in the real numbers, that's just e to the x, e to the y. And sure enough, that's phi of x, phi of y. Therefore, phi is operation preserving, and we can say that the entire group of real numbers under addition is isomorphic to the positive real numbers under the operation. So the next problem is to try to prove that U9 is isomorphic to Z6. This time the mapping is not provided for us, so we're going to have to come up with our own mapping. And the mapping cannot be just draw some lines between the elements. We can't just say let's do this, 1 to 0, 2 to 1, 4 to 2, 5 to 3, 7 to 4, 8 to 5. That's not going to work because, for example, 3 plus 3 is the identity, but 5 times 5 is not 1. So we want to have to do this in a way that preserves the operation. Both of these groups are cyclic. Z6 is generated by 1 and U9 is generated by 2 and others, but we'll take 2 and 1, the generators. I think the best way to find a mapping is to view these groups as sums of 1 and powers of 2. If we look at U9 as powers of 2, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, and 2 to the 6th equals 1. And then we look at Z6 as multiples of 1, 1 plus 1, etc. The mapping becomes a natural mapping that you can see quite easily. Look, let's map, like if we map 2 squared to 2, we're looking at the exponents here. 2 squared, I'll map to 2. 2 cubed, I'll map to 3. 2 to the 4th to 4. So in other words, we're mapping 2 times 2 times 2 times 2 to 1 plus 1 plus 1 plus 1. This is called a natural mapping from U9 to Z6. 2 cyclic groups of order 6. So I'll define the mapping. Let phi map U9 to Z6 by phi of 2 to the n equals n mod 6. To show that phi is operation preserving, we just need phi of xy, but I'm not going to introduce as xy. I'll just say we know every element of U9 is a power of 2. So to show its operation preserving, I'm just going to say phi of 2 to the n times 2 to the m, 2 arbitrary elements in U9, is equal to phi of 2 to the n plus m. And that is n plus m mod 6. And that is n mod 6 plus m mod 6, which is equal to phi of 2 to the n plus phi of 2 to the m. Sorry, that's a bit messy there. But we show that it is operation preserving. Now I'm running out of room here, so I'm going to switch colors so that you can see. I'm going to prove now that phi is 1 to 1. Suppose phi of 2 to the n is equal to phi of 2 to the m. Well, that would mean that n mod 6 is equal to m mod 6, which would mean that 6 divides n minus m, or we could say 6k equals n minus m. Well, if n minus m is a multiple of 6, then we know that 2 to the n minus m is 2 to a power of 6, so it's equal to 1. And that gives us then 2 to the n equals 2 to the m. And so we know that phi is 1 to 1. Now, since the order of U9 is equal to the order of Z6, any one-to-one mapping is also onto. So we don't need to show in this case that phi is onto, because the groups have the same number of elements and we already know that the mapping is one-to-one. So we can conclude then, therefore, I'll do it up here, therefore U9 is isomorphic to Z6. Now we prove that any infinite cyclic group is isomorphic to Z. And you know Z is cyclic. Z is generated by 1 or minus 1. So we know that. Let's just put Z equals, it's a cyclic group generated by 1. And let's let G be generated by some element A, where the order of A is infinite. An infinite cyclic group. So let's write this one other way. G is equal to the set of all A to the n in Z. And all of those powers of A, remember, are distinct. If A has infinite order, then it has all powers are distinct. We prove that. All right, well, I see a natural mapping. Here we have to define the map ourselves. So I'm going to say let phi, and this time I'll just go from Z to G, except I'll write it that way. And the natural map is to let n go to A to the nth power. So let's write that by phi of n equals A to the n. And now we need to show that phi is operation preserving, one-to-one, and onto. So first let's do the operation preserving. So to show that it's operation preserving, we'll start with phi of, operation is addition, so phi of n plus k, let's say, is equal to, by definition of the mapping, A to the n plus k. And we know that that is A to the n, A to the k, and that is phi of n, phi of k. Remember, the operation in Z is addition, and over here it is, well, we don't know for sure, we mark it as multiplication. To show phi is one-to-one, we suppose that phi of n is equal to phi of k for some n and k in the integers. Well, this would imply that A to the n is equal to A to the k. But since G is an infinite group, A has infinite order, this can only happen if n is equal to k. Remember, we proved that in an earlier exercise, that all powers of A are distinct if the order of A is infinite. So A to the n equals A to the k would mean that n has to be equal to k. So we have proven that phi is one-to-one. Phi is one-to-one. And now let's prove it's onto. So to show it's onto, we pick, let A to the n be in our group G. Or we could use this, we don't have to call it G. Let A to the n be any element in there. Well, n is an integer. We know that the definition of G is the set of all powers, all integral powers of A. So then, phi of n equals A to the n implies phi is onto. So that was really easy. So we've got one-to-one, onto, and operation preserving, and we can conclude then, therefore, an infinite cyclic group is isomorphic to Z. Now, we're never going to be asked to prove that a group is isomorphic to itself. The identity map would give us an isomorphism. So, but we will be interested in sets of mappings that are isomorphisms from G to itself. An isomorphism from a group G to itself is called an automorphism of G. So it is a one-to-one onto mapping from G to G that preserves the operation in G. So let's start by looking at an example, and then we will prove that it is an automorphism. Our group will be the special linear group of 2 by 2 matrices, entries from R. In other words, the determinants are 1, and we are going to let M be any matrix in there, any one you want. The identity matrix wouldn't be very interesting, but I mean any matrix. So we fix M, and we define a mapping phi sub M, because it would be a different mapping if we chose a different matrix M. So phi sub M mapping G to G by phi sub M of a matrix being capital M, or matrix M, A, M inverse. We are conjugating the matrix A by M. So I'd like to just look at an example on this slide. Let's let M be the matrix with columns 1, 2, and 0, 1. Then M inverse, you can quickly see, is 1, negative 2, 0, 1. And let's take a matrix A in SL2R, and let's just show what phi does to it. Why don't we let A be, maybe 1, 0, 3, 1. That's in SL2R. And so let's see what phi sub M of A is. Phi sub M of A will be equal to M, A, M inverse, which is the matrix 1, 2, 0, 1, times the matrix A, 1, 0, 3, 1, times the matrix M inverse, 1, negative 2, 0, 1. And you multiply these out, and you will get the matrix negative 5, negative 12, 3, 7. Check it. You'll see that the determinant is 1. It is in SL2R. So you take the matrix M and you just conjugate every single matrix in SL2R, and you just get SL2R back again. We will now show that phi sub M is an automorphism of G, where G is the special linear group of 2 by 2 matrices, and phi sub M is the mapping that sends a matrix A to M, A, M inverse. So first, let's try to prove that the phi sub M is operation preserving. Of course, the operation is the same because this is from G to G, so we have matrix multiplication. Okay, so we start out with phi sub M of AB, and we hope we get phi of A, phi of B. Well, phi of a matrix multiplies on the left by M, AB, and on the right by M inverse. But that's exactly the same thing as MA, M inverse M, times B, M inverse, isn't it? Because M inverse is just the identity. And so we have then, well, we could put parentheses on, like this. And we have phi sub M of A times phi sub M of B. Therefore, it is operation preserving. Now, what about 1 to 1? Well, let's suppose that phi sub M of A is equal to phi sub M of B. That means that M, A, M inverse is equal to M, B, M inverse. So if you multiply on the right by M and the left by M inverse, this quickly gets us A is equal to B, and we know that phi sub M is 1 to 1. Now we need to show that it's onto. These are two infinite groups, So we start to show that it's onto. We let, it doesn't matter what you call it, let's just let A be an element of SL2R. That's we're mapping into that set. So let's see, what would map to it? Well, let's see, if we put A here and we multiply by M inverse on the left and M on the right, that's another matrix in SL2R. And look, if we take phi sub M of that matrix, what do we get? Multiply on the left by M, on the right by M inverse, and we get A. Therefore, every matrix in SL2R is the image under a mapping phi sub M. So we have onto, and we know that phi sub M is indeed an automorphism of G. These are very important properties of isomorphisms, and you should look on page 133 and see the proofs. I think he proves 1, 2, and 4, and 3, 5, and 6 just come quickly from those. I'm not going to take the time in the video to prove them. The proofs will be easy for you to understand. The important thing is to know these properties. That if phi maps G to G prime is an isomorphism, if G is isomorphic to G prime under the mapping phi, then phi always takes the identity of G to the identity of G prime. It always maps identity to identity. Number 2 says that if you take phi of a power of A, it's the same thing as phi of A to the n. That's quickly proved by induction. We know that phi of A squared is phi of A because it's operation preserving, and you quickly extend that to any power of A. 3, if A and B commute, then so does phi of A and phi of B, and vice versa. If phi of A and phi of B commute, then A and B commute. That could be extended really to say if G is abelian, so is G prime then. But here we're just talking about two elements, A and B. Number 4, if G is cyclic and generated by A, that is true if and only if G prime is cyclic and generated by phi of A. In other words, generators map to generators. Number 5, the order of an element is the same as the order of its image. So if the order of A is 5, we know that the order of phi of A is 5. You can use these facts in doing problems, in working within groups, isomorphic groups. If G is finite, then the order of the two groups is the same. Well, it has to be, the mapping is 1-to-1 and onto, so of course the groups have to have the same order. So notice how I put these in words. Identities carry to identity. Powers of A map to the same power of phi of A. If elements commute in G, their images commute in G prime. If G is cyclic generated by A, G prime is cyclic generated by phi of A. The order of A is the same as the order of its image, and if the two groups are finite, they have the same number of elements. Now, these properties of isomorphisms give us some conclusions that we can make about the groups between which the mappings are defined. So suppose that phi maps G to G prime is an isomorphism. It's a 1-to-1 onto map that preserves the operation. Well, if it is, then phi inverse, we know it exists. Phi is 1-to-1 and onto. So phi inverse exists, and phi inverse is a mapping. Phi inverse is a mapping from G prime to G, and it is an isomorphism. If G is abelian, then G prime is abelian. So two isomorphic groups, if one is abelian, the other is. If one is cyclic, the other is. Number 4 says that if K is a subgroup of G, then phi of K is a subgroup of G prime. So we need to know, what does phi of K mean? K is not an element of G, it's a subgroup of G, so we have to define this. This is a set, and it is the set of all phi of x's where x comes from K. So in other words, it's the image of K under the mapping phi. A good exercise for you to do would be to prove that phi of K is a subgroup of G prime. Number 5, if K prime is a subgroup of G prime, then the inverse image of K prime is a subgroup of G. And I've given you the definition of what phi inverse of K prime would be. It's the set of all G in G that map into K prime. So we say it's the inverse image of K prime under phi. And also, number 6, if you apply phi to the center, you know Z of G, the center of G is a subgroup, so it's just like number 4 here. And the phi of K that you get, the phi of the center that you get is the center of G prime. So phi maps center to center. These are all, I would say that you should be able to prove definitely 4, 5, and 6, well, really all of them. But I'm going to leave this up to you. We now have ways to prove that two groups are not isomorphic. D4 is not isomorphic to Z8, and we know that because D4 is not abelian and Z8 is. So that would be one reason. Or we could say Z8 is cyclic and D4 is not. Therefore, they are not isomorphic. We could say that D4 has more elements of order 2 than Z8. Any of these things, anything that you detect like that will immediately give you the groups are not algebraically identical. The Klein 4 group is not isomorphic to Z4 because, well, we could say Z4 is cyclic and V is not. They're both abelian. Yes, they're both abelian, but V has 3 elements of order 2, and Z4 only has 1 element of order 2. They're not isomorphic. U18 is not isomorphic to U10. Well, you would have to take a look at these two groups to see why. You know they're both abelian, so you should check. But the order of U18, is 6, and the order of U10 is 4, so we need go no further. They have different orders. R star is not isomorphic to the complex numbers, the non-zero complex numbers, because in the complex numbers we have 2 elements of order 4. I to the 4th is 1, and minus I to the 4th is 1. We have no elements of order 4 in R star.